Hello. So today we will continue building our CPU. We don't have much left to do. So today we will talk about the program counter again. So in the CPU, there is a program counter which determines what instruction to perform next. And it is in real life, it's just one memory location, one register, one piece of memory. So to add it to our CPU, we go under memory, select register, then we select its 8 data bits, and the label is program counter, PC. So it's a register just like status register or general purpose registers. It's just located outside of all other blocks, and it is used to select instructions from program memory. So, as we spoke before, the program is located in program memory, and we need to be able to read it into the CPU. And the pointer to next instruction is program counter. So initially, after reset, it's just 0. And this is why all programs start from the beginning, because when you press reset button, program counter is reset to 0. So actually, I can just connect it right away to reset signal. So even if I write some value inside, after clicking reset, not only registers inside general purpose register are reset to 0, and also status register, but also program counter is reset to 0. And it outputs 0. So if we connect external memory to program counter, it just selects address 0 in program memory, and program starts from the beginning. And only on very rare occasions, I think in MSP 430 microcontrollers from Texas Instruments, I think the program counter resets to all ones, and the beginning of the code is actually located at the end of the flash memory for these one particular type of microcontrollers. But as far as I know, all other microcontrollers start program from 0. Okay, so clock signal, basically what it does is on each clock signal, the processor reads one instruction, performs it, and on the next clock, it takes the next one. So how does it do it? It does it through program counter. On each clock signal, program counter should increase by 1. So under arithmetic, I can select adder. We could use our own 8-bit adder, but let's use this built-in adder. Or let's check out, maybe we can use our own 8-bit adder. It's just a little bit bigger and requires more signals. So let's use it like this. So we need to connect program counter to our adder input A, and we can connect a constant number 1 under wiring constant, and we select that it is 8 data bits. Value is 0x01, and we connect it here. And carry in is 0, so I select constant 0 facing south, and I connect it to this adder's carry in, so that it's just 0 plus 1 plus program counter. And I can directly connect it to data input. And let's see what happens. So program counter is 0, but it's connected to this adder, which adds 1. So the output of this adder is 1. So when we make a clock, this program counter will receive the new value, which is previous value plus 1. And on the next clock cycle, it's going to increment by 1 again to 2 to 3 and so on. We just need to select, also attach the clock signal. So I take clock signal from here and connect it to program counter. And enable signal should be 1 at all times. So I take a constant and its value 1, connect it here so that the program counter is enabled all the time. So let's see. When I do clock rising edge, as you can see, program counter incremented by 1. On falling edge, nothing happens. So it is 1. 1 plus 1 is 2. So 2 is directly fed into program counter. And since it's D-type register, D-type flip-flop register, on rising edge of the clock, it reads the value that is shown to its data input. And since it's always the output plus 1, basically clicking clock just increments program counter by 1 every time. And so we have a program and clock ticks and program counter ensures that program is read by 1 instruction every time and advances by 1 instruction every time. So program counter is the one that makes sure that all lines of code are executed in their written order. Okay, so I can click reset and program counter is reset to 0. Now, regarding the program counter, there are two special ways how program counter also works. So program counter tells which is the next instruction to be performed. And in normal cases, it just advances by 1. But we have two special instructions, which are called jump, which basically is jump to a new location in code. So for example, we have, I don't know, we have some function or some other thing that we want to perform. So we want to jump to a new location in our code. Jumping might not seem intuitive at the beginning, but the second thing that a program counter needs to perform is branch, BR. It is branch. It is branch to a new location in code if some condition is met. So branching basically is if then else implementation. So for example, you have a code and if A is greater than 0, then add 1 to B, or if else if A is smaller than 0, subtract 1 to B. For example, if A greater than 0, you want to, for example, do B++. And else, you want to do, for example, B minus minus. So how is it done inside the microcontroller? It first compares A to 0. If true, it performs B++ and jumps over B minus minus. So we are using branch and jump. And if this condition is false, if a is 0 or less, it jumps over b plus plus, it branches to this b minus minus location. And so branch is the same as jump, except branch happens only if the condition is met. For example, some flag in status register is set or clear. For example, in this case, we compare a to 0. If a is positive, it means that negativity flag is 0. So perform this if n flag is clear. And the other option you need to perform, n flag is set. So we compare a to 0, and if negativity flag is clear, it means a is greater than 0, and do this and jump over the second option. Otherwise, branch to the second option. And so basically, these instructions, what they do is they manipulate program counter. So instead of doing every line, program counter needs to jump over some lines of code to some further location, or do some code and then jump over some lines of code so that the other condition is not executed. So program counter needs to do this, and to do it, we need to manipulate it a little bit. So let's go back to our logisim, and we will actually delete this connection between program counter and program counter plus 1, because we can have other conditions here. So the new location to which to jump is going to be defined by the instruction itself. So for example, if n flag is clear, instead of program counter being plus 1, it should be, for example, plus 5 or some new value. So this new value will actually be hidden inside the instruction. So right now, we can just put a multiplexer here for program counter, which selects between program counter plus 1 and some new value. So I go to plexers, multiplexer, then I will configure it in the following way. Select bits are going to be 1, data bits are going to be 8, and it will be facing top right. And include enable is no. So east, top right, 1, 8 floating, and no. So here, if the multiplexer selects 0, I'll actually just put some control, which I will call the following way. I will name this control as jump and question mark. So basically, if this is true, let's see. Something not right. Reset simulation. Simulation enabled. So if jump is 0, it means don't jump, just add 1 to program counter. And if jump will be high, it will select some new value to load into program counter. And we will actually put it here. It is an 8-bit input, and its name will be new instruction or new PC, new program counter value. And it goes into the second input of this multiplexer. So, for example, if jump is true, then the new value of program counter should be 82. So when I do the clock, instead of program counter +1, it loaded a brand new value. And this will be used in branch and jump. It will tell you how far to jump over some instructions. And if jump is false, then clock increments program counter by 1. As you can see, it goes 56, 57, 58, and so on. And if I set a new value and set jump to true, then on the rising edge, it jumped to a different new value. If I select another one, then on rising edge, it jumps to a new value. And if I select jump question mark to 0, then it just adds 1. So this control will select whether we need to jump or whether we need to just execute the instructions normally. And now let's check out how we can automate this jump signal. So if we have instruction jump, then it needs to set jump high always. If it's branch, then we first need to compare the flag with the value that we want it to compare with, and only then select if we force jump or not. So the possible values of this branch, there are actually 8 different branch cases. So, and we can check them out in this document, which is on Artus. So what kind of branches do we have? We have 4 flags: 0, carry, negativity, and signed overflow. And we can force branching either if each of these flags is 1 or 0. So if 0 flag is 1, then branch. If it's 0, then branch. If it's not 0, then don't branch. And so on for carry, true or false, for negativity, true or false, and for signed overflow, true or false. So we need to compare the value that we wish the flag had with the real value from status register. So here in status register, we take the status register output and we feed it into a splitter. So we split these 4 bits into 4 separate bits. So under wiring, I select splitter, and fan out is 4, and bit width in is also 4. And now if I, for example, set status register value to 5, which basically means that 2 of the flags are high and 2 are low. So 5 means signed overflow flag is set, negativity flag is set and carry bit is set also. So if status register has value 5, it means 2 of the flags are set and 2 other flags are cleared. And then I need to AND the status register value with the value that I wish the flag had. So I select multiplexer, which is facing west. Its control is in top. Select bits are 2 because we have 4 different flags, so 2 inputs. And data bits is just 1 data bit per channel. And including enable is no. So if I connect this multiplexer, it outputs the flag that I select. So I need a 2-bit control, which data bits are 2, and the name of it is flag select. So I'll call it like this, flag selector. So for example, when it's 0, 0, it selects flag number 0. I'll just write it down so that we know in what order these flags came. So it's V, N, Z, C. So I'll write it here, V, N, Z, C, so that we know which flag is which. So bit 0 is signed overflow. Oh, sorry, they are actually written in the opposite manner. So C is bit 0, Z is bit 1, N is bit 2, and V is bit 3. So for example, if we want to branch, if carry bit is set, it's high, so I select flag number 0, which is carry flag, and then I need to compare it to a value that I wished the flag had. And comparing means and. So if flag is the same as we wish, then output should be set. Wait, is it and? Here is a little bit different symbol. This is XOR. Ah, now I get it. Okay, sorry, it's not and. So another control that we will have is flag compare value. So here I put an input, which is flag compare, the value of flag that we wish it had. And if flag value that we wish the flag had is the same as real value of flag, then we should get high value. And if they are different, we should get low. So which arithmetic logic function has this property? If A equals to B, then set high, and if A not equal to B, then set low. Which one would it be? So A and B, 1, 1, 0, 0, 0, 1, 1, 0. So if they are the same, output should be high. If they are the same here, also high. And if they are if they are different, then output should be 0. Well, it's X nor. So basically, it's XOR with inversion, because XOR is if bits are different, set high. If they're the same, set low. And in this case, they're just inverted. So I take XOR under gates, X NOR gate. I put it here. I select gate size narrow, number of inputs 2, output value true false, no label, and so on. And it's facing west. So in this case, if let's see what the value of this is. So if we want the flag to be high, and it is high, for example, we select carry flag 0, they are equal, so this thing outputs high, so it's true. So we need to force jumping. And if they're opposite, if, for example, we want the flag to be high, but flag is actually low, then this XNOR gives us also low. So this simple schematic compares some value that will be coded inside the instruction read from the flash memory with the actual value of status register. And if they are true, if they are equal, it will set output high. And if they are opposite, then it will set output low. So with this, we can compare bits. And then this will be used in our branch instruction. So if flags are the same, then force jump. But for jump instruction, we don't care if the flags are equal or not. So we need to add OR to this output and a new control signal, which will be called force jump. So I select gates OR facing west, size narrow, number of inputs just 2. I put it here, and I put a new control signal, which is called force jump. And I connect it. Okay, let's put it a little bit prettier, like this. So like this. And this output will be connected here to this jump signal. Actually, we can probably select location bottom left so that we don't have to run these cables over each other. So I'll put it like this. So now we have created a schematic which can force program counter to take a new value if some condition is met, or if we want to force it to jump to a new location. So I'll just reset the processor. So right now program counter is 0. And force jump is 0. This is a little bit wrong. We would need another signal. So we have XOR, we have this, and we have this. And the name of this is force jump, force program counter +1. Okay. So because right now in this condition, we have a situation where flag is, some of these conditions can be true even if we don't want to jump. So we need to add another layer of controls, which is a multiplexer, which selects between whether we want to jump or whether we want to make program counter add 1. So I will put an multiplexer which is facing west. Its controls are located, for example, bottom left. Select bit is 1, data bit is 1, and include enable no. So here, with this multiplexer, we will select whether we want to jump or branch, or we want program counter to add 1 regardless of output of these other bits. So first input will be just 0. wiring constant, facing west, value 0, like this. And the second input here. And this yet another control, which will be facing west, will be called force PC plus 1. And it will be facing west, yes. Like this. So this will control this multiplexer. So, and it ends, or better would be to call it enable jump. Enable jump branch. So now this program counter schematic is complete. So if enable jump branch is 0, then output to this multiplexer of program counter will always be 0, and program counter is calculated as program counter plus 1. Now, if we enable jump or branch, then the output of this jump branch logic is forwarded to program counter. For example, let's say we set force jump high. Then regardless of value of this comparison, jump is always true, and program counter will be forced to this new value 218. So on rising edge of the clock, program counter obtained a new value. Now, if force jump is set to 0, then jumping is determined by flag and flag compare bit and such register result. So right now we want flag to be high. It's in reality low. For example, let's compare it to negativity flag, which is 0, 1, 2. So 1, 0. They are different. So the output is 0. Or with for jump is also 0. So right now, since flags are different, jump doesn't happen. Program counter just increments by 1. And if flags are the same, for example, we compare flag with 0, it's true, then this true is forwarded to program counter selector, and program counter is forced to jump. So it jumps to a new value A, address A. So if we disable jump, then program counter is incremented by 1. And I know it might seem overwhelming initially, but you do it once, all CPUs have this function, this logic, and later you just use it as is. And to control all of these signals, we'll just make a big table, go through all possible values of these bits, and control them through instruction decoder in the next lecture. So right now we have created a logic which either makes program counter to increment by 1, or if we enable jump and force jump, then it will jump to new value. For example, right now, it just jumps to this new program counter value. Or if we don't force jump, then the result is determined by flag comparison with the real flag value. So they're different, so jumping doesn't happen. And if they are the same, for example, status register bit is set, then it jumps to the new value, for example, to this value. So using these, I don't know how many, 1, 2, 3, 4, 5 bits, we control program counter. And this is how microcontrollers jump to different places in code depending on some conditions. Okay, so I hope you could follow through. Otherwise, just copy this schematic, and that's all for this lab.